Dear students, let us continue our video lectures on Advanced Digital Signal Processing course. Let me share the screen. In this video lecture, let us discuss some of the frequency domain analysis of linear time invariant systems. We will introduce some of the new terminologies that are referred to different kind of systems, mainly looking at their frequency domain content or frequency domain aspects. So let us start the discussion. So before we get on to the discussion on different categorization of the systems, let us start with, say, in frequency domain analysis of the systems. What are the possible ways of analysis, frequency domain analysis of linear time invariant systems? So assume that we have an LTI system, okay, for which x of n is input and y of n is output. As we know, the output is related to input through a convolution sum of the impulse response of the system, where impulse response h of n is obtained when input is impulse and its response to the system is what is referred to as impulse response. Okay, and this initial response that we obtain for impulse referred to as impulse response. This initial assessment will help us to analyze the system for any other inputs x of n through the convolution sum of x of n and h of n. Okay, in frequency domain, how do we represent the system? How do we represent? We have actually the frequency domain representation given by h of e power j omega, which is obtained by discrete time Fourier transform of h of n, right? So, and thus you can know that y of e power j omega is equal to x of e power j omega into h of e power j omega. Okay, this is one kind of frequency analysis for the systems. The other domain in which we analyze the systems is in Z transform. H of Z, this is defined for broader class of inputs, input signals, analysis of the system for broader class of inputs, and then Y of Z is similarly obtained by X of Z into H of Z. Okay, these are different ways of analyzing the system in frequency domain or in time domain. Now let us see the relation between h of e power j omega and h of n. How do we obtain? Assuming h of n is aperiodic, okay, n equal to minus infinity to infinity, we find the correlation with minus j omega n, right? So correlation with complex exponentials. Okay, so h of z similarly we obtain through correlation of h of n with z power minus n, where z equal to r e power j omega, right? So this is defined for broader class of systems as well as signals to analyze, okay, even broader class of signals and systems than what is defined with Fourier transform. See, as you notice, when we do the correlation or projection of the signals onto the exponentials, the nature of exponential itself is complex. Okay, and hence it's likely that h of g power j omega or h of z, okay, are also complex. Okay, and thus what will happen when we want to represent h of z? Okay, how do we represent? Mod of h of z and then angle of h of z. Similarly, to represent h of e power j omega, Okay, it will have mod, that is absolute value of the spectrum and angle of the spectrum. Okay, so far we have seen the relation between time domain to frequency domain, or time domain to Z domain, or time domain to discrete time Fourier transform, discrete Fourier transform, discrete Fourier series, and so on. Okay, now we will see using the frequency information or the spectrum of the transfer function of the system, okay, of an LTI system. Okay, we what what information or what assessment can we make on the system? Is there any things that characterize the system? We have seen the characterization of the system using impulse response, okay, or the transfer function in the initial classes in terms of the causality, stability, and so on. We will see even little more variants of such things. Okay, in practical applications as well, how does this frequency spectrum will help us? Okay, to design a better systems, or so to compensate some of the issues that happen because of the transmission and so on. Okay, so let us see. So for discussion of the analysis that we do now, let us take a simpler example. So let us consider some of the frequency selective filters. Okay, the systems defined by some of the frequency selective filters. That is, say h of e power j omega has a specific nature. That means it passes some of the frequencies of the input signal and attenuates some of the other frequency content of the signal. Okay, let us introduce filters. See, assume that h of e power j omega, as we said, is equal to 1 for mod omega. What is the range of h of e power j omega to be defined? Or what is the range of omega in which h of e power j omega has to be defined? For minus pi to pi or 0 to pi. So let it be equal to 1 for less than or equal to omega c and 0 else. That means this spectrum, discrete spectrum, looks like this. Okay, minus omega c and omega c. Up to what extent should we sketch it? Up to pi and minus pi. Okay, so assume that this is the spectrum h of e power j omega. And here for this spectrum, it is a zero phase spectrum. That means there is no phase term. So magnitude itself is directly h of e power j omega is real. Okay, and now what we wish to get is, this is referred to as low pass filter. The reason being, it passes the frequencies, okay, with no attenuation, and it attenuates all the frequencies beyond omega c. Okay, that means it suppresses whatever is in the input signal. Say if x of e power j omega has some spectrum, okay, ranging again minus pi to pi. Okay, the x of e power j omega has spectrum something like this. Okay, what does this filter do? So this is x of e power j omega. It passes the frequencies which are less than omega c as it is, and then attenuates the rest of the frequencies. That means put 0 in place of the rest of the frequencies, right? And then it passes the rest. Yeah. Right, it's like this after filtering. Okay, this is y of e power j omega. Okay, so now what we wish to get is, if this is in frequency domain, how does it look like in the time domain? Okay, we want to just find out what is h of n. Through inverse Fourier transform, inverse discrete time Fourier transform, we can find it. And you can see that it will be equal to sine omega c n by pi n. Okay, I'm not computing here. You can write the discrete Fourier, inverse discrete Fourier transform relations, and you can find it. Okay, where h of n is equal to integral of h of e power j omega e power j omega n d omega, right? Minus pi to pi. Okay, and this is equal to h of n is equal to 1 by 2. Okay, using this you will be able to see this. Okay, right. So now you can see that this h of n is from where to where? It ranges from minus infinity to infinity. Okay, and so on. So this is, so in fact this is discrete. So though I have sketched it as continuous, in continuous signal, as continuous signal, it is in fact discrete. Okay, please note that. Okay, and so on. Okay, so 0, 1, 2, 3, 4, and so on. Okay, so based on omega c, it will like this point will be decided. Okay, fine. So now let us see if this is h of n. What can you comment about the causality of the system? The question is the system 1. Okay, this is system 1, assume that. Okay, is system 1 one causal? Okay, and stable also you can tell, but more importantly here, is it causal? The answer is no. Why? The reason being, h of n is not equal to 0 for n less than 0. Okay, what is the condition for causal systems? The impulse response has to be 0 for n less than 0. Right? So, and hence it is not a causal system. So, it is non-causal system. Impulse response and system. And hence, what is the implication? So, this is referred to as ideal low pass filter. So, what is the implication? Can we realize ideal low pass filter? The answer is no. Can we realize means practically can we have an ideal low pass filter, something like this with 0 phase, especially here. zero phase. Okay, the answer is again no. Okay, to make it realizable, that means, see, if I write y of n, which it depends upon x of n, convolution with h of n. See, if h of n is non-zero for n less than 0, that means that y of n depends upon x of n plus, okay, n plus n naught terms. Okay, and hence it is not possible to practically have it. We don't know what will happen after n naught, right? So you can't put the value of y of n now. Okay, based on what will happen in x of n after 10 samples ahead. Okay, so for that reason we can't realize it, and hence this is not practically possible, and hence to realize a low pass filter, what should we do? Okay, so it's realizable only if and only if we have a phase delay. Okay, if we have some phase delay, if we introduce some phase delay, we'll be able to introduce it. Okay, we will be able to realize it. So now let us discuss, okay, how to introduce the phase delay. Okay, so see, assume that time domain system which does delay. Okay, I just want to sketch here x of n and y of n. What is the system or the impulse response of the system that creates delay? Delta of n minus n naught. Okay, so if this is the system, n minus n d we may say, or n naught we may say. Okay, if this is the system, what will happen? This introduces how much delay? This introduces is equal to what? E power minus j omega n d. Right? When we substitute in that and simplify in discrete time Fourier transform expression, we get that, okay, for all omega. Okay, for this system, this is what we have. Okay, so we would like to have a delay, and at the same time, why is this delay for? This delay is not to center it at x equal 0. Okay, instead of centering at this location, we would like to center this. See, if this is the region where roughly non-zero terms of the impulse response of the low pass filter are there. Okay, we instead of sitting like putting it 0 here, we would like to center it here. Okay, and this is in fact ND then. Okay, so that's what we wanted to do through introducing the delay to make a realizable low pass filter. Okay, and hence how do we define now? For H low pass, okay, e power j omega, thus we can define 1 into e power minus j omega nd for which region? Mod omega less than or equal to omega c, and 0 else, because 0 into whatever phase delay also is 0. Okay, this is how we define a ideal low pass filter. If we consider this, what will be in time domain? Okay, this implies e power minus j omega and d in for mod omega less than or equal to omega c and 0 else. This is the ideal low pass filter. Okay, ideal and realizable low pass filter. Okay, it may not be completely realized, but the terms, some of the terms in the negative direction may be 0, close to 0. So we will be able to realize. Low pass filter, okay, with, okay, that can have causal approximation. Causal, okay. Fine. So now let us write in time domain, what does it happen? See the delay here, how does it reflect in time domain? It reflects to sine omega c n minus nd by pi into n minus nd. Okay, this is how it reflects. Okay. Okay. So now let us see. Okay. How as you can see, it starts from here. So roughly in this region it is close to 0. So you can approximate up to here and you can realize. Okay, this is how we do, even though it extends from minus infinity to infinity. And to have a practically viable low pass filter, we will even truncate it. Okay, beyond like in negative direction as well as from 2 times nd. Okay, to preserve the symmetry in the spectrum. So 0 to nd and nd to 2nd roughly. Okay, so that's how we truncate it, and this we can consider starting from here to here as the practical approximation of the low pass filter in time domain, and that reflects slightly in somehow in the frequency domain. That we will bother how does it reflect in the frequency domain and so on while we discuss on the filter design. Okay, for now it is enough to understand that the low pass filter essentially has this kind of frequency spectrum, and to make a causal low pass filter, okay, what we usually do is we introduce a delay. How much delay again depends as a design parameter or criteria. Okay, and now let us define the high pass filter. Okay, what is high pass filter? The filter that passes the high frequencies is referred to as high pass filter. Okay, if you wish to define in frequency domain, okay, how do we define? H high pass filter, okay, e power j omega. See, it does exactly opposite operation as that of the low pass filter. Okay, that means if we have something like this, okay, so it passes these frequencies. Okay, again this passes these frequencies. Okay, and then from here, okay, minus omega c to omega c, it doesn't pass. Okay, let this be say minus pi, and let this be pi. Okay, so this passes these high frequencies and doesn't pass the low frequencies. So it is roughly, this is the magnitude spectrum. Okay, magnitude spectrum of, okay, magnitude mod of h of high pass e power j omega. Okay, so now later we will worry about the phase aspect, but without much worrying about the phase aspect, how do we define low pass filter, high pass filter? We can simply define it as what? As 1 minus of, okay, h low pass filter, because wherever high pass filter, low pass filter doesn't pass, it will pass now. Wherever it passes, it doesn't pass now. Okay, and hence the h in time domain, how do we write it? Delta of n minus h low pass filter of n. This is how we define. Okay, so now considering with zero phase, what do we have? Delta of n minus sine omega c n by pi n. Okay, this is how we can define for the high pass filter in time domain. Okay, so when we have the delay, same delay will occur even here. So it is defined as high pass filter. If you want to define explicitly, okay, we define h high pass e power j omega as, okay, 0, that's right, e power j omega nd for mod omega greater than omega c, okay, 0 else. Okay, this is how we define. Okay, if for this, what we can define is this is 1. Okay, if there is no phase delay that we write. Okay, this is one. This is how we define high pass filter. Okay, so now let us discuss on another property or another aspects of this system design using the frequency domain characteristics. We have assumed that we have a system which gives y of n from x of n, and the impulse response is h of n, and frequency response is h of e power j omega or h of z. Okay, see, what I wish to do is I want to design a inverse system. See, what is an inverse system? This is the system. I want to design inverse system. Okay, how do I design this inverse system? Okay, how do I design it? So I should have a anyway some inverse system. Assume that somehow I design. See, if it is exactly the inverse operation of this initial system, what I'm expected to get at the output. The first system gives x of n to y of n, and if this is exactly inverse operation, it does exactly inverse operation, so I should be able to get x of n back, right? So what does it mean? See, these two can be considered as cascade of two systems. Okay, when two systems are in cascade, okay, and what is the, say, I'm giving x of n as input and getting x of n as output. Okay, and this effective impulse response is equal to h of n convolution with hi of n, right? And this x of n is itself is output. So if I want to get this from x of n itself, what should be the impulse response h of n? X of n has to be convolved with delta function, then only you will get x of n here. This implies the h of n is equal to delta of n, which is equal to h of n convolution with h. Okay, please note this h of n is different. So we write h effective of n. Okay. So the inverse system should say, if I convolve the impulse response of the inverse system and the original system, what I'm supposed to get is the delta function. Now let us see in frequency domain. What should it be? See, what should happen in frequency domain? I should say, for this, if I take the frequency domain representations, what will happen? H of e power j omega into h inverse of e power j omega inverse system frequency response is equal to 1. This implies h inverse system, okay, free spectrum of the inverse system is obtained by reciprocal of the original system. Okay, frequency response of the original system. Similarly, h of z into h I of z is equal to 1, imply h I of z, okay, inverse system is equal to 1 by h of z. Okay, so now let us take a small example to see this. Okay, let h of z is equal to z inverse minus half by 1 minus 0.9 z inverse. Okay, and let this be a causal LTI system. Okay, and hence, since it is given that it is causal, this is the example. Okay, since given this is causal, what is region of convergence? ROC is equal to mod z greater than 0.9. Okay, in this case, see if this is h of z, like what will be h inverse of z is equal to simply 1 inverse of 1 by h of z, right? 1 minus z inverse by z inverse minus half. Okay, so now the question is, what should be the region of convergence for this system? Okay, so the region of convergence for this system, how do we decide? So what are the possible region of convergences for this system? Say for initial discussions, let us take this as okay equal to 2. Equal to 2. Okay, sorry. Okay, so z inverse, right? So now what is possible region of convergences with this? So one is possible ROC. Okay, let me take to the next space. ROC can be mod z greater than half or mod z less than half. Okay, which is the correct ROC? That's our question. Okay, so what do you think is the ROC for this? The ROC, see if we should have the multiplication of h of z into hf inverse of z to exist, or the convolution sum of h of n and hi inverse of n to exist, there should be some region of overlap for the ROC. Even for this, there is a region of overlap that is needed, and hence the ROC of h of z and hi of z should have a region of overlap. Okay, there should be some to define, so to have a defined h of z. Okay, hi of z, ROC of h of z and hi of z must have overlap. Okay, that implies the ROC of h inverse of z here is equal to is mod z greater than half, right? So that means the causal system here, in fact causal and stable system here, give rise to the inverse system that is also causal and stable in this example. Okay, and hence hi of z is also causal and stable. Causal will write here. It's also stable, as you can know, right? Now let us take another example. Okay, let now the in this example 2, h of z we have is equal to z inverse minus half by 1 minus half z inverse. Okay, sorry, just 1 minute. Let us take this as 0.9 z inverse, exactly same thing that we have taken before. Okay, but here z inverse minus half. For this, again, let this be a causal system. Okay, h of z corresponds to a causal system. Okay, so and hence this implies that ROC is okay mod z greater than 0.9. Okay, and hence the let us see what will happen to this inverse system and what is its ROC. Okay, hi of z, now if we write, what is this? 1 by h of z, which is equal to 1 minus 0.9 z inverse by z inverse minus half. And hence, what are the possible ROCs here? possible ROCs are mod z greater than 2 and mod z less than 2. Please note that z equal to 2 in this. Okay. So mod z greater than 2 and mod z less than 2. Of course, there is z term 1 minus. So these are the possible ROCs. Okay. So z equal to 0 may also be inclusive. Okay, in some cases. Okay, but let's leave it. So now, among these two, which do we suggest as the possible ROC? Say, if we consider the case 1, we have, see, for both of them, we have the overlap with respect to the z greater than 0.9. And hence, both are possible ROCs in this case. However, okay, if we consider case 1, that is H inverse of z has transfer function which is given like the z transform given by this, but the ROC is mod z greater than 2. Okay, it implies that it is causal system. But is this a stable system? But not stable. Why is it not stable? Because it ROC doesn't include z equal to 1. Okay, so the initial system, if you see, it is a causal system and stable system. Okay, so you can note from here that the inverse of the stable system need not be like causal and stable system need not be a causal and stable system. Okay, so now let us take the second case. Okay, wherein you have h of z inverse of z is equal to 1 minus by z inverse minus 2, where minus half. Okay, where ROC is mod z less than 2. Okay, here you can see that the system is causal or not. System is not causal. Okay, because the ROC is not extending outside, but it is stable because it includes the unit circle. So in either of the case here, okay, it is neither like not inverse system hi of z is not causal and stable, even when while the h of z is causal and stable. Okay, so it's not necessarily that a system having causal and stable h of z or the frequency response need not have its inverse system to be causal and stable. And if it has causal and stable inverse, then it is like in previous example, then it is referred to as minimum phase system. Okay, we will see the properties of this minimum phase system. But if okay, h of z is causal and stable and okay, further, and h inverse of z is also causal and stable. Okay, this is and it's very important. H inverse system is also causal and stable. Such system is called, okay, such system is called or referred to as minimum phase system. Okay, we will see in more details why this name minimum phase system is given to this. Okay, but such systems are very like important class of systems. Okay, and those are referred to as minimum phase systems. Why do you think such systems are important class of systems? Okay, let us now discuss more on minimum phase systems. Little bit more on minimum phase systems. Okay, so why do you think these kind of systems are important? Because see, if I see in some of these, many of the scenarios, in fact, I may need to design, I may be demanded to design the inverse system. See, for example, if I have a communication channel, say I'm sending some information XFN, okay, through a communication channel, and this is a communication channel. Okay, see, usually what will happen, channel will add some noise or it may add some distortions, and because of that what I get output will not be exactly same as whatever I transmit. So the distortions created by the channel are referred to as channel impulse response. Okay, they are modeled as channel impulse response. And these distortions may be blur sometime or noise sometime and so on. Okay, so thus the output signal that I get is input and the convolution of channel impulse response. Okay, but for many of the practical purposes, what I wish to get is not the degraded signal after the communication channel, but I would like to put a virtual system, okay, that mitigates the effect of the channel. Virtual, okay, I am calling it as inverse. You can we will see why it is called inverse system, okay, that mitigates the effect of channel. Why? Because I want XFN here, that is the exact information to be obtained. So this is another, like this is modeled as HI of n to have the X of n back from Y of n. Okay, I want from Y of n X of n back. How do I get it? If I convolve with, okay, HI of n, what will happen now? So if I see the output Y2 of n now, okay, so Y2 of n, if you see Y of n convolution with, okay, the inverse system output, which is equal to X of n convolved with H of n and convolved with Hi of n, okay, and hence what I will have is, this is nothing but the delta n, okay, and what I get is X of n. Okay, so usual practice is to design an inverse system for the effect of the channel, okay, and referred to as compensator. This system is referred to as compensator. Okay, this compensates the effect of channel, okay, for channel, to mitigate the effect of channel. Okay, okay, so now the question is, see, in channel can be modeled with some impulse response and we will get corresponding H of z. Okay, ideally what we wish to have, the inverse system that we model, okay, should also have causality and stability. For all practical reasons, a system only if it is causal, okay, then only it is realizable. Okay, and if it is stable, then only it is controllable. And hence, for all the practical reasons, we wish H of z, okay, we wish H of z and Hi of z, okay, to be causal and stable. Okay, for practical reasons. Okay, what do we mean by practical reasons? H of z is causal, means it is realizable. Okay, causal implies it is realizable, whereas stable imply it is, okay, controllable in some sense. Okay, so we need these aspects for practical implementations, and hence H and H. So this is possible. Okay, possible. Okay, that means we would like to have both of them causal and stable possible if and only if, okay, H of Z is minimum phase. Okay, as I have as I just discussed now, the system is which has causal and stable, which is causal and stable, and which also has causal and stable inverse is referred to as minimum phase system. Okay, so for many of the practical regions, we prefer to have minimum phase systems. Okay, or see, in some cases, it may not be possible to have the minimum phase system. So in that case, we would like to find out the equivalent minimum phase system for a given system. Okay, that will help us to model or to design the compensation systems and so on. Okay, so now in the next video lecture, let us discuss also how to, if this system is not minimum phase, how to design an equivalent, like equivalent means having the system with same magnitude response, okay, but having minimum phase characteristics. How do we get it? Also, let us see, for a given magnitude response, is there only one possibility for the system having only same magnitude response, or many possibilities? Let us explore this in the next video lecture. Thank you.